In this section, we're going to talk about vectorized operations. Let's start with the where statement. We have an array that goes from 10 to 50, and we're checking which values are greater than 25. Those values, 30, 40, and 50, will be assigned a 1. When we print the result, you can see that 30, 40, and 50 are all greater than 25, so each of them gets a 1. This kind of operation is useful for creating features in machine learning models. For example, if age is greater than 25, we could assign it a 1, and otherwise assign it at a 0. Now let's look at the put function. This function requires you to specify the index first, followed by the values you want to replace. It's often used for data imputation when there are specific values in your dataset that need to be changed. For instance, in some CRM systems, missing data might be represented with the number 999, and you might want to replace that with an actual value. In this example, we have an array, specify the index positions 1 and 2, and replace them with 6 and 7. When printed, you can see those replacements clearly. Next, we're talking about reshape. Here, we have two arrays, a 1-dimensional array and a 2-dimensional NumPy array. The 2-dimensional matrix has a shape of 2 by 3, meaning 2 rows and 3 columns. Remember, the brackets represent rows, and the values inside represent columns. If we reshape a 1-dimensional array into 5 by 1, we get 5 rows and 1 column. In this case, there are 5 brackets, 1 for each row, and a single value in each representing 1 column. Earlier, it was the opposite, 5 columns in 1 row. The number of elements inside each bracket represents the columns. If we transpose the matrix, we swap the rows and columns. So 1, 4, 2, 5, 3, 6 becomes the new order. The transposed matrix now has a shape of 3 by 2, the reverse of the original 2 by 3. Transpose operations are common in linear algebra, especially when multiplying matrices, and we'll see examples of that later. Now, let's look at the resize function. The array we're working with has only 5 elements. When we resize it to 2 rows and 3 columns, NumPy repeats the values to fill all the slots. Since there are only 5 elements, it goes 1, 2, 3, 4, 5, and then starts over from 1 to fill the remaining space. This can look strange if you're not paying attention to the number of elements in your array. That's why it's important to always keep track of your array's size. Being aware of the number of rows and columns is especially important during data processing. If you start with a large data set, say 1 million rows, and end up with only 10,000, you need to understand why. Anyone reviewing your work will want to know what happened to the missing rows, especially if you're doing data cleaning or transformation. Keeping track of shape and size is a good habit to maintain data integrity. In this example, the temporary array shape is 2 by 3, 2 rows and 3 columns. Now, let's talk about Ravel and Flatten. Both functions take a multi-dimensional array and convert it into a single axis. One-dimensional array. For instance, if we have a 2 by 3 array and apply Ravel, we get 1, 2, 3, 4, 5, 6. The resulting shape is one-dimensional with 6 elements. Remember, if the array has 2 dimensions, it's a 2D array. If it has 3, it's a 3D array. We can also modify the flattened array. For example, if we replace one of the values with 99, that change will be reflected in the flattened version. The Ravel function actually modifies the original array, which can seem a bit strange at first, but that's exactly how it works. When we flatten an array using Ravel and set the first index equal to 99, it also changes that value in the original array. That's how Ravel behaves. The flatten function, on the other hand, does the same kind of flattening, but without modifying the original array. That's the main difference between the two. We can flatten arrays in different ways, row by row, which is called C-order, or column by column. For example, when we flatten row by row, the output might look like 90, 9, 2, 3, 4, 5, 6, going left to right across each row. If we flatten column by column, it goes top to bottom within each column, giving us 90, 9, 4, 2, 5, 3, and 6. To give you a more practical example, imagine we have a grayscale image that's 3 by 3, 3 rows and 3 columns. We can use Ravel to flatten that image into a one-dimensional array. In machine learning, this is common when you need to feed image data into a model, such as a neural network. For example, flattening a 8 by 20 8-pixel image from the mice dataset, which is a popular dataset for beginners, turns it into a single row of values that can be processed by the model. Now, let's look at some vectorized mathematical operations like addition, subtraction, multiplication, and division. These operations work element by element. For example, when we add arrays column-wise, we might get results like 1 plus 4, 2 plus 5, and 3 plus 6. The same pattern applies to subtraction, multiplication, and division. There's also a function called NumPy Vectorize, which applies a scalar function. That is, a function operating on a single value to every element in an array efficiently. For example, suppose we have an array from 1 to 5 and define a function like x squared plus 2 times x plus 1. This function is applied to each element individually. For instance, for x equals 1, we calculate 1 squared plus 2 times 1 plus 1, which equals 4. It's important to follow mathematical order here. Exponents first, then multiplication, then addition. Next, let's talk about broadcasting, which is a very powerful feature. Broadcasting allows you to perform operations between arrays of different shapes without having to manually reshape them. Without broadcasting, you'd have to adjust one array's dimensions to match the other. But with broadcasting, NumPy automatically expands dimensions where possible. For example, when adding 4 plus 1, 2, and 3, the result becomes 5, 6, and 7. That's NumPy automatically aligning shapes so the operation can happen. Even if the shapes are different, NumPy still performs the operation efficiently. For instance, multiplying arrays of different dimensions results in values like 4, 8, 12, 16, 20, and 24. The same logic applies to addition. Now, let's move on to sorting, another useful operation. Sorting is often used when you need to order data, such as arranging dates chronologically or sorting people by age from oldest to youngest. It's a common function when cleaning or preparing data. For example, sorting an array from lowest to highest might give 1, 2, 3, 5, 9. You can also sort along different axes. For instance, sorting row-wise might produce 1, 3, 4, 2, 5, 9, 6, 7, 8. Sorting column-wise rearranges each column individually. For example, 3, 5, and 6 in one column, 1, 8, and 9 in another, and 2, 4, and 7 in the last. Another related concept is argsort, which sorts by index positions instead of values. Suppose we have the array 3, 1, 4, 1, 5, 9, 2. Argsort returns the indices that would sort the array. For example, 1 is at index 1 and index 3, 2 is at index 6, 3 is at index 0, and so on. These indices correspond to where each value belongs in sorted order. You can also use sorting with strings. Strings are sorted alphabetically by default. For example, if we have names like apple, banana, blueberry, and cherry, and we sort by index using argsort. We can then reorder the original dataset accordingly. The sorted order would be apple, banana, blueberry, and cherry. Apple comes first because it starts with A, followed by banana and blueberry, both starting with B, and finally cherry with C. If we look at the sorted indices for this example, they might be 1, 0, 3, and 2 corresponding to the alphabetical order. So to wrap up this section, that's how flattening, vectorized operations, broadcasting, and sorting work in NumPy. In the next section, we'll continue exploring more advanced vectorized operations.